So in this video, we're going to give an overview of what an implicitly defined function is. So here I have two functions of x, y equals 2 over x, and x times y equals 2. And the idea is that both of these functions describe the same function of x. And in fact, the graph of the function y equals 2 over x is shown right here. So the difference between an explicit function and an implicit function is simply this. If the function is explicit, then y has been isolated or solved for. So here the y is isolated. I have y equal 2 over x. In this example, the y has not been isolated, so the y is implicitly defined. If I wanted to take the derivative of this, say I have x times y equals 2, and I wanted to take the derivative of both sides with respect to x, what I would generally first do would be to divide both sides by x to get y equals 2 over x, which manipulates it into the explicit form where y has been solved for. And then I would take and bring my x up like we've been doing by changing the sign on the exponent. And then I would go ahead and get my y prime, or remember y prime is the same as dy dx. I'd get my y prime equaling negative 2x to the negative 2. So in general, if a function is implicitly defined and you want to find the derivative of y prime, or dy dx, you solve it so that the y is explicitly defined. You solve it so that y has been isolated. The problem is that we can't always do that. So in the next example, I have a relation. I have the relation x squared plus y squared equals 9. And in this case, I don't have a function. I can see that I'm not passing the vertical line test if I inspect things graphically. And the idea would be, well, what if I want to know the equation, for example, of the tangent line when x is equal to 2? And the problem is, of course, when x equals 2, there are two possible outputs on the graph. Again, this graph is not a function, it's a relation. And so what would I need to do? Well, what happens if so it's implicit because y hasn't been solved for. Here's y sitting here buried in that squaring function. And the question is, what happens when you try to solve for y? So you get x squared plus y squared equals 9. What would happen if we tried to solve for it? Well, we would subtract x squared from both sides. And then I would take the square root of both sides to cancel the squaring off of the y. But we need to remember that when we take the square root of both sides, we get a plus or minus the square root. So I don't get a single function. We don't get one function. We get two functions, plus or minus. So on the next slide, what we can see is when we try to solve it, we get that y equals plus or minus the square root of x squared minus 9 from the previous slide. That actually gives us two separate functions. One is the positive square root, one is the negative square root. And the negative square root of 9 minus x squared actually represents the lower half of the circle. And the lower half of the circle by itself is a function of x. It does pass the vertical line test from pre-calculus. And the positive square root does pass the vertical line test. So it is a function. So when we have the circle x squared plus y squared equals 9, the idea is that y is defining implicitly two separate functions of x. So if I wanted to know the equation of the line that's tangent to the circle when x is equal to 2, I would need to tell you whether I wanted the tangent line in quadrant 1, or here x is equal to 2, I would need to tell you that whether I wanted the tangent line in quadrant 4. So quadrant 4. And depending on the quadrant I was after, I would depend on the derivative I need to take. Either I take this derivative or I take this derivative. So a big question is, do I need to be able to solve for y in order to find the derivative if I want to know the slope of a line on a graph at a particular point? And so the last slide kind of gets at this a little bit stronger. Here I have an implicitly defined function. I can see I have a y cubed term, a y squared term, and a y to the first term. And it's implicit because y hasn't been solved for. And in fact, over here, explicit, I have question marks because if you tried to solve it for y, you won't be able to. And so what if you wanted to know the equation of the tangent line or the derivative when, say, x was equal to 4, and you can't solve it for y? How do you find y prime? Because in order to find the equation of a tangent line, you need the derivative. So the whole purpose of this homework assignment is to learn how to take derivatives implicitly. And when we implicitly take derivatives, the tool that we're going to be using is the chain rule. And the goal of the homework is going to be able to find derivatives without having to solve for y. Because one, sometimes it's easier to find the derivative without solving for y, and two, sometimes you can't solve for y, and we need a technique for finding derivatives when we can't solve explicitly for the variable y.